Okay, please start.
Okay, well, welcome back for the second installment. So today is going to be a more formal lectures with definitions, and mostly I'm going to be introducing some techniques and notions that we will actually use in the course of the proofs of the main results. So for some of the experts here, it will be a bit boring, but I know there's a bit of a varied audience, so it's probably worthwhile introducing these. So I plan to talk to, at the very least, about singularities of the minimal model program, canonical and log canonical models, and about multiply ideal sheaves, and hopefully a little bit more. So let's start with the singularities of the minimal model. So most of the time, I'll be dealing with normal varieties. So one nice feature about normal varieties is that they're smooth in codimension 1, regular in codimension 1. So I can pick U to be the non-singular locus, and this is what we call a big open subset. So what does that mean? Being a big open subset means that if I look at its complement, x minus u, then the codimension in x of the complement is greater or equal to 2. Now, on the non-singular subset, you know how to make sense of the canonical line bundle. And then you define the canonical line bundle on x just by taking the canonical line bundle on u and pushing it forward. So here I is the inclusion from this big open subset into x. This is a reflexive sheaf. It's actually equal to its double dual, and it has several nice properties. But it can also be somewhat threatening. So mention that. For example, it could be non-Q Cartier, which would be a problem. So notation-wise, as I mentioned before, Kx, a canonical divisor Kx, is any divisor such that the corresponding divisorial sheaf is isomorphic to omega x. So of course, this is not uniquely determined. Now, what is a log pair? So a pair xb is a log pair if, well, first of all, x is a normal variety. B is an R divisor. So by bi, I'm denoting the prime components of this divisor, and these little bi's are the corresponding coefficients. So this has to be is an R Weyl divisor. So it's just a formal linear combination with real coefficients of codimension 1 subvarieties. And the most important property that I'm going to insist on is that Kx plus b should be R Cartier. So R Cartier means that locally, you can write this. This is the same as a linear combination with real coefficients of zeros minus poles of rational functions. So I already mentioned that if K of x is not Q Cartier, that's sort of intimidating. But I'm insisting that this mixed object be R Cartier. This is very friendly. For example, you know how to pull this back automatically because it's a linear combination of 0 minus poles of rational function, and to pull back a rational function, you just compose with whatever your morphism is. So there's really no issue. And also, intersection theoretically, if you want to calculate the intersection of this with a curve, you just restrict every function to the curve, compute its degree, and then sum with these coefficients. So this is a very friendly condition. If that condition fails, you have to start thinking hard, probably. OK, so now we want to figure out how to measure the singularities of log pairs. Maybe I should, in most situations, typically, the coefficients, but not always, as we'll see in a second, these coefficients are between 0 and 1. If the coefficients are allowed to be negative, we usually preface this by a sub-pair of some kind. Well, I'll try to make it clear when the coefficients are not between 0 and 1. Okay, so in order to measure the singularities, we need to think about log resolution. So this is really over the complex numbers. So log resolution of a pair XB is a proper birational morphism f from, what notation do I want to use? Let's say y to x, such that, first of all, I want that the exceptional divisor of f, so the exceptional locus is a locus where sub variety of y where this is not an isomorphism. I want this to be a divisor. So in particular, it has to have codimension 1. And when I look at the f minus 1 lower star of b, so this is the proper transform of the divisor b plus this exceptional divisor, this has to have simple normal crossing support. And I really mean simple normal crossing in this time. So each component is a smooth divisor, and they intersect transversely. And I didn't say it, but it should be clear that y has to be smooth in this picture too. Okay, so that's a log resolution. It may be a pain to, given a pair, to write down the log resolution, but in practice you can do it in most cases of interest, and they always exist in characteristic 0 by Hironaka's theorem. Okay, so once you have a log resolution like this, then the natural thing to do is to compare the pullback of kx plus b. So this is an R-Cartier divisor. Pulling it back makes sense. You want to compare it to k of y. And so you write the difference between these two objects is typically written as plus ay of xb, where this guy here is known as the discrepancy. Okay. So the coefficients of this is a divisor. Its coefficients could be positive or negative. So this divisor is of form sum over some prime divisors. So coefficients, let's say AP, depending on x and b. Pretty soon I'll suppress the x and b times p, where p are divisors on y. And for all but finally many divisors on y, this number is 0. In fact, this number is non-zero either on exceptional divisors for the map from y to x, or on those divisors contained in the support of b. In which case, the value of the discrepancy is just minus the coefficient of b. So discrepancy is, morally speaking, minus the coefficients on y. Okay, and so we measure these singularities in terms of these discrepancies. So maybe make one more definition, then I can tell you what the various singularities are. So the total discrepancy of xb is the infimum of the set of all possible discrepancies where p is any prime divisor over x. So in order to compute the total discrepancy, you have to worry about all possible resolutions of x. Right? So there are infinitely many possible divisors that may play a role. And in fact, sometimes this really is the infimum. We'll see this example in a second. And this is the total discrepancy. The discrepancy of the same pair is the infimum. It's almost the same thing But here, we only think about P, which are prime divisors exceptional over X. So we're considering exactly all of the same divisors, essentially, except the ones that lie on X, most importantly, except the components of B. Okay, so the idea is that smaller discrepancies should correspond to worse singularities. So the bigger the discrepancy, the better your situation. Maybe let me skip that remark. First of all, let me give you the definition. So in this spirit, we define the following singularities. So first of all, we say definition. So XB.
Excuse me, is it ever clear that this is always a negative number?
That the discrepancy is always a negative number? I didn't say that.
No, of course not.
No, but okay, so let me get the definition and then I'll do some examples. And there's sort of one value that's a clear breaking point, and that will be clear from the definition and the first example that I'll do. So yeah, so far it's unclear what these values are. If you're thinking that this should be sort of minus the coefficient, you are thinking that these numbers should always be negative, but that's not the case. Okay, so definition, XB is log canonical, respectively, Kawamata log terminal, if the total discrepancy so log canonical greater or equal to -1, and Kawamata log terminal is if it's strictly greater than -1. And we say that this is canonical, respectively terminal, if and only if the total discrepancies, not the total, the discrepancies are greater or equal to 0 and strictly greater than 0. Okay, so those are definitions. It's unclear that they're useful, and it's sort of unclear why we chose -1 and 0, at least in first approximation. Hopefully, I'll do enough examples and applications of the theory that it will become clear. So let me show you why -1 really is a breaking point. So remark, if the total discrepancy or the discrepancy is less than -1, then it is -infinity. So as soon as you have a discrepancy that's smaller than -1, corresponding to a coefficient that's bigger than 1, then actually you get coefficients that are arbitrarily big or discrepancies that are arbitrarily small. So let me do proof by example. Let's start with, after I perform some blow up, I end up with some component of my divisor B with coefficient 1 plus epsilon. And I'm going to try to argue that by performing further blow-ups, I produce coefficients that are bigger and bigger, and hence more and more negative discrepancy, right? So this is coefficient 1 plus epsilon corresponds to, if this is my divisor P, AP is equal to -1 minus epsilon. So what you can do here is you can take, maybe P is not smooth, so let's just take a general point on P, a smooth point on P. Then we can blow it up, and it's very easy to see what the new coefficient is. So if we call this x and we call this x prime, trivial computation shows that, and let's say that this is map F, the pullback of k of x plus one exceptional divisor. So let's here denote the exceptional divisor, and here's the strict transform of P by P prime. The pullback of K of X plus, so the canonical class of X prime is given by the pullback of K of X plus the exceptional divisor E. So now, what happens to this divisor P? Well, when you pull it back, you're going to get a strict transform P prime plus E, the exceptional divisor, again, with coefficient 1 plus E, epsilon, right? So the pullback of Kx plus 1 plus epsilon P will now be equal to Kx prime plus 1 plus epsilon P prime. We're not doing anything to the P prime, you're just taking the strict transform. But now, the exceptional divisor will come with a coefficient 1 plus epsilon coming from the pullback of P, and minus 1 coming from this E, right? So the discrepancy of blowing up a smooth point is 1. If you put it on the other side, the corresponding coefficient is minus 1. So you get epsilon E. So the new picture, we have multiplicity 1 plus epsilon here, and multiplicity epsilon here. Now it's clear we have not produced anything with worse discrepancy, but now we blow up the intersection point by an identical computation, which I won't do in order to if we blow up this, we get a second exceptional divisor. Let's call it F. The coefficient of E will now still be epsilon. The coefficient of P double prime, let's say, will be 1 plus epsilon. But now, when we do this blow up, the coefficient of this divisor F will be 2 epsilon. There's an extra contribution coming from this multiplicity epsilon on this divisor here. So now clearly when I blow up this point, I'll get something on multiplicity 3 epsilon. Repeat this as many times as you want. You get multiplicity n times epsilon for n as big as you want, and hence you get discrepancy as negative as you want. So, you can set that. You can easily prove it by induction in any dimension with this basic idea. And essentially, the only thing you need to do is you need to know how to compute the discrepancy of, so in general, if you have a pair X, B, let's say that this is smooth, and this is simple normal crossings, and you blow up some center Z, let's say smooth center, contained in the intersection of the components BI, then the corresponding, you get one exceptional divisor, and the corresponding discrepancy is very easy to compute, so it's similar to the computation we just did. So the contribution from, forget about the divisor B, the contribution from X, what you would get by comparing these two, depends on the codimension of the center that you're blowing up. In this case, we blew up something of codimension 2, and we got coefficient 1. If you blow up something of codimension 3, you'll get coefficient 2, and so on. So you'll get a contribution just from X, which will be the codimension in X of Z minus 1, right? But then, so that in some sense, the higher codimensional center, the better the corresponding singularity. Well, it's a smooth point, so there's not really a singularity to talk about. However, there's a contribution of these BIs, so there'll be a minus sum of BI, where the coefficient, so where BI contains Z. I'm assuming that they're smooth. If they're not smooth along Z, the contribution may be bigger. This is sort of the simple normal crossing contribution. Okay, so that's why the threshold -1 is important, and canonical versus terminal, that's a little bit more of an accident. So let me sort of illustrate why this is nice. So here, if it's, let's say, canonical, implies that when I take any resolution, I can write that ky is the pullback of kx plus this discrepancy divisor ay, where by definition, all discrepancies are greater or equal to 0. So this is an effective divisor. It's not a mixed object. It's every single coefficient is greater than 0. It follows that by the projection formula that the sections of mky are actually identical to the sections of mkx. Right? Because I'm looking at rational functions that when I add them to ky, I get something effective. Well, that's the same as adding them to this gadget and getting something effective, but you can read off the same answer down on x where these divisors disappear. So if you think that through, that will tell you that these set of sections match. And in particular, this gadget that I claim was important, the canonical ring of y is isomorphic to the canonical ring of x. Now, clearly, that's an important feature. So maybe we would like to know how can that be salvaged in, for example, the log canonical or the KLT case. Right? So in the log canonical KLT case, we will have, again, that ky is, so let's assume, for example, that xb is log canonical. Ky will be the pullback of kx plus b plus this divisor ay. Now, this divisor ay is a bit problematic. It has a positive and a negative part. So let's write this as, so in certain references that I'm using, the way that this is decomposed is as ey minus ly. I don't know why we wouldn't use by, but anyhow. So where ey and ly are effective, and ey ly is equal to 0. So this funny symbol means the biggest divisor that's contained in both of these. So what this means is simply ey and ly have no common components. All right, so all I'm doing is I'm taking the stuff in ay with positive coefficient, I'm putting it here. With negative coefficient, I'm putting it here. And actually, it's pretty easy to see that the stuff with positive coefficient is always exceptional. And the stuff with negative coefficient may not be exceptional precisely because the push forward of ly will be equal to b. So we set up things so that the push forward of, we pick this canonical divisor such as push forward is equal to klx. And then the push forward of my ly will be equal to b. And the push forward of ey will be equal to 0. So now I just simply rewrite this formula as ky plus ly is equal to the pullback of kx plus b plus ey. Okay? Now, if I started with something log canonical and I take a log resolution, the coefficients of this divisor are less or equal to 1, and it has simple normal crossings. So this is a nice log canonical pair. And moreover, when I look at sections of any multiple of ky plus ly, well, maybe, yeah. Maybe for simplicity, let's assume that you have rational coefficients and that this m clears the denominator, so we don't have to think too hard about what the symbol means otherwise. It would just mean the round down. So this will be, of course, it's the same as sections of m f upper star of kx plus b plus m ey. But now this is an effective exceptional divisor, and this is the pullback of, if I've cleared denominator of a Cartier divisor downstairs. So by the projection formula, this is just h0 of m kx plus b, telling me that essentially I can replace any log canonical pair by a log smooth pair with simple normal crossings without losing any information about the canonical ring. Right? So if you're really opposed to log canonical pairs, think that they're just log smooth pairs where the divisors have simple normal crossing intersection. Okay. I've already mentioned that these, so the definition is remarkably simple. You just have to look at one log resolutions. So log canonical and KLT can be checked on a single log resolution. Log canonical and KLT conditions, it's a theorem, can be checked on any given log resolution. So it's quite easy to check these conditions. You make it have simple normal crossing and you just look at the coefficients. And the remarkable thing is that they have mild singularities. I'm not going to prove it, but it's not hard to prove that KLT singularities are automatically rational. And log canonical singularities, well, the next best thing there, Dubois, whatever that means. I'm not going to define Dubois. Well, I should probably do some example of at least one non-trivial, not completely trivial example of singularities. So everyone's favorite singularities are cones. So one example is, let's say that x is a cone over a rational curve of degree n. Then, so here's my horrible picture of a cone. There's a vertex v. Let's blow it up. Blowing up the vertex v, we get another surface, which is now smooth, with an exceptional divisor e. So this is my x. This is my y. This is my f. It's just a blow up of the vertex. That's a log resolution. So I can compute, on this log resolution, I can compute how singular this surface is, or the singularity in the neighborhood of this point is. And so the way that this is done is typically as an application of a junction. So what's easy to check is that the self-intersection of this exceptional divisor is minus n. You can view it as a Hertzsprung surface with a curve, negative sectional self-intersection minus n, and you're contracting that down to a point. Okay, and now somehow you want to solve, you want to figure out when you pull back k of x, how many copies of E you get. What's the coefficient of E? So you use a junction because you see this E is, by assumption, a rational curve. So then minus 2 is the degree of the canonical class, which you can compute by a junction. It's a smooth curve on a smooth surface by intersecting k of y plus E with itself. Now, this, you see, k of y is just the pullback of k of x plus a of E times E, right? And the pullback of k of x will intersect E trivially. So this will tell you that you get a of p plus 1, right? In terms of intersecting with E, this is mute, so you just get a of E plus 1 E squared, so it's going to be minus n a of E plus 1, as long as it didn't make any stupid computation mistakes. And so you read this off, you get that a of E is just minus 1 plus 2 over n, so that these are indeed KLT. And as n gets bigger and bigger, this is approaching this bad threshold, this minus 1. Right? So they're KLT, but as n gets bigger and bigger, they are more and more singular. Which seems, right, the singularity is more interesting as n gets bigger and bigger. A similar calculation will tell you that if you now, instead of assuming that the genus is 0, if the genus of E is 1, if it's an elliptic curve, then you get a log canonical singularity. And if the genus of E is greater than 1, the same computation tells you that it's in fact not even log canonical. The other typical example that I'm supposed to do at this point is computation of the log canonical threshold of a cusp. So I'm supposed to tell you what a log canonical threshold is before I do that. So lost my notes, so I'll use a definition which the definition will be correct. The notation may or not be standard. So how can you compute a log canonical threshold? Well, suppose that we have xb a pair, and probably you want to assume that the coefficients of b are between 0 and 1. Maybe let's assume that it's at least a log canonical pair. And let's say that we pick m, some effective R-Cartier divisor. And then we're going to consider the log canonical threshold of the pair xb with respect to this divisor m. This is probably not the right standard notation, but I think everybody will understand what it means. So it's going to be the biggest, the supremum of those positive real numbers with the property that if I consider the pair x, comma, b plus tm, that this is log canonical. So, okay, so if I pick m to be 0, this is not interesting. Let's just assume that m is non-zero. Then for some sufficiently big value of t, it will be not log canonical, and there'll be a threshold where it becomes log canonical, a maximum value of t where it becomes log canonical. So the typical example of this is the log canonical threshold of C2, no boundary, with respect to the cusp. And I know the answer, so if we make a calculation mistake, I can spot it. We're supposed to get 5/6. So this is supposed to point to you that log canonical thresholds are an interesting, this is a smooth variety. There's no singularity here. So this log canonical threshold is only measuring this singularity. And it's an interesting measure of this singularity, right? It's certainly not measuring the multiplicity. The multiplicity is 2, right? So it's measuring something else that's going on. So while it's measuring the log canonical threshold, we'll find out later why this is so important. So what do you need to do? Well, in order to compute, we need to decide if this is log canonical or not, so we need to work on a log resolution. And fortunately, you can work on one log resolution that works for both b and m at the same time, then this coefficient is not going to cause problems. It's not like you need to choose a different log resolution for every value of t. So how do you do this? You start with C2, and you look at the cusp in here, you put it in there with coefficient t. And now we repeat the computation that I erased, where we sort of blow up until we get simple normal crossing, and we keep track of the new coefficients that we get. So let's blow up a first time. So when I blow up the first time, I get a new exceptional divisor, which is a copy of P1. Let's call this E1. It's a copy of P1. And you can do this. You can write this in local equation. So this is y squared minus x cubed. You write down the two charts of your blow up, and you substitute this in. And what you get is that actually the first blow up desingularizes this. It makes it look like a parabola. However, it's a parabola tangent to this exceptional curve. So if this is my curve C, then I'll just denote by C its strict transform, sort of abuse notation here. Now, the curve C will also appear with coefficient T. What will be the coefficient of the exceptional divisor? We're getting a -1 from just blowing up. That's the difference of the two canonicals, as we saw before. So there should be -1. However, there's also a contribution coming from the curve C. Since the curve C has multiplicity 2 at the origin, you have to add 2t. Okay. Now, luckily, that's not a log resolution, so we have to keep going. The next step is to blow up the only place where stuff is not simple normal crossing, the origin. And we get a new exceptional divisor, E2. And then we get the strict transform of E1 and the strict transform of C. They intersect in one point, right? Because they both have the same tangent direction at the origin. Now, the coefficient of E2, we get a -1 coming from the fact that we're blowing up a smooth point. And then we get a contribution. Both of these curves are smooth at that point, so you don't have to weight their contribution. You get a contribution of -1 plus 2t from this curve and t from that curve. So plus -1 plus 2t plus t. So the upshot is that this contribution is -2 plus 3t. So finally, we get the simple normal crossing situation by blowing up one more time. Since these now have all different tangent directions, you get a simple normal crossing situation. And the coefficient of the third exceptional divisor is going to be, well, we get a -1 from the relative canonical. Then we have a -2 plus 3t from this divisor, a -1 plus 2t from that divisor, and finally a t from the curve. So all told, we have a -4 plus 6t. Okay, so now what's the log canonical threshold? This is a log resolution, so I can tell by looking at the log resolution. I'm looking for the biggest value of t for which this is log canonical. So that's the biggest value of t for which all of these numbers are less or equal to 1. So this number, it's clear that -4 becomes a 5 plus 1, so you get t is 5, 6. And then you check that plugging in 5, 6 in any of the other ones, you get something that's strictly less than 1. -1 plus 5, 6 times 2, well, do the computation. I've done it several times before. Yeah, you can trust me. I've also made mistakes on this. I got them 4, 6 for some reason, occasionally. But okay, so these log canonical thresholds are easy to compute. And the reason that they're important is that something interesting is happening. In this case, something interesting happens along the locus where you get your log canonical singularity, your non-KLT singularity. So suppose that we have a divisor, let's call it AP, of XB, for which the discrepancy is less than -1, respectively less or equal to -1. Then we say that P is non-log KLT, respectively non-log canonical place. So it's a divisor where the condition of being log canonical or the condition of being KLT is being violated, and I switched them. I knew I was going to do it. Right? This is violating greater or equal to -1 would be log canonical, so that's being violated, not log canonical. Similarly, it's not greater than -1, so it's not KLT. And remember, if F is your map from Y to X and P is a divisor contained in Y, then F of P is non-log canonical or non-KLT center. And these are interesting. They'll play a significant role in applications of Nadel vanishing. Okay, so I think there's a couple more flavors of singularities of the minimal model program that you can't get without. Do without. We already have 4, log canonical, KLT, canonical, and terminal. There's also PLT, semi-log canonical, and DLT that I find it hard to work without. But I don't think we need them immediately, so I'll come back to them if and when we need them. Okay, so now I can, with this notation, I can state a more precise version of the theorem on finite generation that I mentioned the other day. So that, again, this theorem is due to Birkard-Cascini, Hacon, McKernan, and also to Sue. So this is finite generation of the canonical ring. So suppose that we have XB is a KLT pair. I should say projective pair, let's say. Now let's state it more in general. So it's a KLT pair. And let's say that F from X to Z is a projective morphism. So I'm going to state it in the relative setting because I will need it in the relative setting. And let's assume that kx plus b is actually Q Cartier. Let me make sure. I typically assume that b is effective, but let me sort of emphasize that it's effective. Then the relative canonical ring is, so what is this object? For every integer m, you can consider the push forward of ox m kx plus b. So you may be slightly intimidated by this because you may think, well, these are Q Cartier divisors. They don't have an integral coefficient. So what does this symbol mean? Well, what it means is you just round down those coefficients, take the greatest integer that's less or equal to that. If you think through the definition, that's what it automatically means. Or you can just think of this object as only being defined for m sufficiently divisible so that that is actually an integral divisor. So if this is the first time that you run into this, you just want to think of those as being integral divisors. You're not really losing anything. So you can push these forward. And these are going to be sheaves of rings over O of z, over the structure sheaf of z. And as an algebra over O of z, you ask that this is finally generated. Is finally generated. So the typical example is z is affine. Or even better, z is spec of the structure sheaf, then what you're asking is that the canonical ring, the direct sum for m greater or equal to 0 of h0 m kx plus b is finally generated. Right, because if z is affine, then the push forward is just determined by the global sections as a z module. As an OZ module, so if it's affine, it's spec A as an A module. Okay, so that's what the result says. Now, conjecturally, this should also be okay for log canonical pairs. But I really need to emphasize conjecturally. This is a very deep conjecture. It's pretty much equivalent to if I remember correctly, it's equivalent to the abundance conjecture, or at least very close to it. So it seems like a very small step to go from Kawamata log terminal to log canonical. After all, your sum coefficient is changing from greater than -1 to greater or equal to -1. But the feeling that this has is actually, the corresponding log volume form is going from being integrable to being non-integrable. So something really bad is happening at that moment. So conjecture is still everything should work in this context of log canonical pairs, but it's certainly tough to verify. Yes?
Excuse me. We don't need that kx plus b is big or big?
No. So I'm just claiming, I'm not claiming that I can do flips and divisorial contractions and get a minimal model. I'm just claiming that the ring is finally generated. So there's a technique due to Fujino and Mori that says that essentially you start with any KLT pair, you look at the eta calibration, right? So up to some changing things birationally, you can look at the eta calibration, and then the pluricanonical ring of this pair is finally generated if and only if some corresponding ring on the eta calibration is finally generated, if you know what the eta calibration is. And the ring on the eta calibration is always of general type. So essentially what I'm saying is that improving this, you can assume that it's of general type because of this trick due to Fujino and Mori. Okay. Well, maybe it's better if I don't write it down because then I have to tell you a little bit about the eta calibration, which is not very difficult, but it's easier to discuss the eta calibration once we know that the ring is finitely generated. So once you know it's finitely generated, you can always consider proj of this ring. So maybe let's assume that x is projective. Let's not worry about stating everything in the relative setting because it's exhausting. Assume x is projective, and so we're just working with z as spec k. And then this ring is finitely generated. I can take proj of this ring, and let's say maybe call it W. And so we get a rational map from X to W. This is just what I called, this is just defined by sections of a sufficiently high multiple of Kx plus B. So that would probably, in the notation of previous lecture, would be phi of some multiple of Kx plus B. So this is the map defined by the sections.
This is definitely too small for me to.
Okay, so I didn't think. Okay, so you can ignore this because it's written here, right? I sort of decided to show you where it lands in. So it's defined by sections of one of the graded pieces of this ring where the graded piece is sufficiently big. That's the whole point of being finitely generated. And since it's finitely generated, it could be defined by any successive multiple. And using that fact, you can deduce fairly quickly that W is normal. And one very interesting case is suppose that the dimension of X is equal to the dimension of W. So the dimension of W is easy to check. That's just K kappa of X, the quadratic dimension of X. So if these two things are the same, then one can check that this map, X to W, is actually going to be birational. So a priori, you'd expect it to be generically finite, right? They have the same dimension. It may have generically some positive degree, but it's more or less this business that, if you have a finite map and you pull back an ample divisor, it is still ample. So if maybe sections of one multiple cannot give you generic degree 1, all you need to do is pick a sufficiently high multiple and you will actually get generic degree 1. So that's not hard to show that it's birational. And so maybe in this case, maybe I can call this X sub can to say the canonical model of X. And then I have a new pair, X sub canonical and the corresponding divisor, which is just obtained. So if this map is phi, it's just obtained by pushing forward this divisor B. Then this gadget here is actually a log canonical model. So what does log canonical model mean? It means that, in other words, it's a log canonical pair. Or actually, if I start with a KLT pair, it will be KLT. Okay? So the singularities do not get worse when I take the log canonical model. And K, this log canonical class, is ample. That's what a log canonical model is. Okay, so there's one small thing that you have to check is that the singularities didn't get worse, right? So why do we expect that the singularities, and you also have to check that this gadget is ample, right? So let me not do all the details, but the idea is the following. Let's suppose, and you can easily fix it into proof, that kx plus b is base point free. So there's a moving part plus a fixed part, where the moving part is base point free. So being base point free means that the sections of the corresponding line bundle have no common zeros. So you get an actual morphism to X canonical. And you see, in this case, it's easy to check that the push forward of this divisor corresponds to the push forward of this divisor plus that divisor. But f is exceptional once you assume that it's generated in that degree. That automatically forces that f has to be exceptional. It's an easy check. And M will be the pullback of O x canonical 1 of the corresponding hyperplane bundle. And so O x canonical 1 will just correspond to the push forward of kx plus b. In other words, to the log canonical class of the log canonical model. And finally, if we compare these two, then kx plus b. Oh, this cannot be right. There has to be a coefficient of k in front. And when we compare these two, kx plus b will just be the pullback of kx canonical plus b canonical plus this fixed part, this effective exceptional divisor. So this tells you, right, that so the discrepancies of this are made up by this mixed object, f minus b. But the coefficients of b, by assumption, if this is KLT or log canonical, the coefficients of b are less than 1 or less or equal to 1. So when I take them to the other side, I get something with coefficients greater than -1 or greater or equal to -1. So it automatically, once this, you verified this formula, and of course there's a 1 over k. Get that right? Once you verify this formula, then automatically it has canonical singularities. But also, since this is an exceptional divisor, it's also automatically true that the log canonical ring of kx plus b is equal to the log canonical ring of its canonical model. So in other words, I didn't lose any information. So you really are free to work with your original pair or the corresponding canonical model. And this canonical model really gives you a distinguished representative of the rational class, which keeps track of all the information of the original variety. So maybe for those who don't know this already, maybe I should also remind you. So in the case, how does this work out in the case of surfaces? In the case of surfaces, you do this very geometrically. You start with your favorite surface, then you produce a minimal surface, and then you produce a canonical surface from it. So you start with x, your favorite smooth surface, projective surface of general type. Then you apply Castelnuovo's criterion, and you construct the minimum model. So Castelnuovo criterion does what? It blows down -1 curves. I'm never sure why it's -1 curve. Is it because k of x intersect this curve? So -1 curves. K of x intersect the curve is equal to -1, or e squared is equal to -1. They're always smooth rational curves that you blow down to smooth points. Yes?
No.
Oh, you were just yawning. OK, so that's how you produce a minimal model. Each time you do this, the Picard number goes down by 1. So eventually, you get rid of all negative curves. And here you get that the minimal model, canonical class, is still a smooth surface. And the canonical class is Nef. So kx minimum dot any curve is always greater or equal to 0. But unluckily, as I mentioned before, canonical models, even for surfaces, actually have mild singularities. So to get your canonical model, now you can blow down rational curves which are sort of 0 curves. So the intersection with these exceptional divisors is actually going to be 0. So you blow down k trivial curves, and then you end up with mild singularities. But the great thing that the canonical class is ample. And of course, this will have what we call terminal singularities, which for surfaces at terminal means smooth. And this will have canonical singularities. which for surfaces means rational double points. So I'm trying to bypass the story of flips and divisorial contractions because I won't really need it. You can do the same thing in high dimensions. You start with your favorite smooth n-fold of general type with some effort, but pretty much using just the finite generation theorem in the way it's stated. But there's some effort. We need to discuss extreme arrays, etc., and give a bunch of definitions. You can produce a minimal model. So this is given by finitely many flips and divisorial contractions. So divisorial contractions look very much like, well, they are blowing down a codimension 1 subvariety, very much the analog of blowing down these -1 curves. Flips is a completely new operation where you contract some locus, but then you produce a singularity that's not admissible, so you have to sort of extract some other locus to make it admissible. So it's a much more complicated procedure. If you're topologically inclined, it reminds a bit of a den twist or something like that. This typically has terminal singularities. So it will be singular in codimension greater or equal to 3. And K is NF, intersects every curve non-negatively. And then now you actually have a morphism down to the canonical model where this has typically canonical singularities. And Kx canonical is ample. The minimal model is not necessarily unique. They're pretty well understood, but it's not necessarily unique. So these other two singularities that I introduced naturally appear when you work, instead of working with log pairs, you just work with varieties with no boundary. But it's really important to be able to work with log pairs if you want to prove things by induction, right? So if you've seen classification of surface, you always end up playing with some curves on the surface. Well, that's pretty much a log pair, right? And in high dimensions, well, we have to do something similar. OK, so why is this theory so successful? Well, and why doesn't it work in characteristic P? Well, the main reason is because these definitions are sort of set up to apply something known as Kawamata-Vivek vanishing, which is an extremely powerful tool, and the whole subject depends on this tool. So when we try, this vanishing result is known to fail in characteristic P, and so when we try to do things in characteristic P, it causes, well, there are many problems, but this is the biggest headache of them all. So very, very little is known in characteristic P. So maybe you're familiar with Kodara vanishing. So Kodara vanishing, I don't think it's easy to prove. There are both analytic and algebraic proofs, but I don't think there's any proof that you can sort of give in one lecture comfortably. I think a couple of weeks is more adequate. So it's not an easy theorem, but it's been known for a long time, and there are several proofs of it. So let's say that you have X, some smooth projective variety over the complex numbers, or at least a field of characteristic 0. And let's say that we pick A, an ample divisor. So an honest divisor with integral coefficients, if you prefer, think of it as a line bundle. Then all higher cohomology of Kx plus A always vanishes for every I greater than 0. So I don't know, how old is Kodara vanishing? Is it from the 60s? Does anybody know? It's been around for a while. Does 60s sound right to you? Maybe. OK, I should have checked it out. So this is not particularly useful for us because in this context we have these log pairs. They're rarely going to be smooth. So we need a generalization of this result, which is known as Kawamata-Vivek vanishing. So actually, given Kodara vanishing, the proof of Kawamata-Vivek vanishing is not as difficult, but of course you'd have to dream that this statement is useful, and you'd really have to want to prove it, first of all, and then you'd have to find the right tricks. So it's a version of Kodara vanishing that works for Kawamata log terminal pairs. So assume that we have some Kawamata log terminal pair. So if you didn't like what we did so far, you can just assume that this is simple normal crossing pair, and the coefficients are strictly less than 1. You can make that assumption. You won't lose much at all. And let's assume that L is a Cartier divisor. Think of it as a line bundle. And let's assume that L minus kx plus b is big and nef. So I've already defined both of these concepts, but let me remind you. Nef means that it intersects any curve non-negatively. And big means the big part, you can think of it as just saying that L minus kx plus b, top self-intersection, is positive. It has positive volume, this divisor. Multiples of that divisor have many, many sections. OK, so you're in this situation. Maybe you should think of this as being a birational version of ampleness. If you have a birational map and you pull back an ample divisor, it's no longer ample, but it certainly is bigger nef. Any pullback of a bigger nef divisor is bigger nef. It's really easy to check. So all of our theory is supposed to be birational. This works much better in the birational setting. Then the higher cohomology groups of L vanish. Maybe I'm supposed to put an exclamation mark. This is going to be really important and useful for us. So I have one quick question for Gino. How long is this lecture supposed to last?
Sorry?
How long is this lecture supposed to last?
2.5 hours.
2.5 hours. OK, so we're definitely going to need to take a break. Let me let me say a few more words, and then we'll take a break. So let's see. What do I want to say about Kawamata-Vivek vanishing? Well, once you have Kawamata-Vivek vanishing, a relative version follows easily. Relative version follows easily. You may worry, why do we even need a relative version? Well, for example, we'll be worrying about families of varieties of general type, so maybe we'll want to do something in a relative setting. So also, when you try to construct these flips and divisorial contractions, it sort of naturally happens that you have to do things in a relative setting, unluckily. So in the relative setting, what will you need? So instead of having a smooth projective, a projective KLT pair, I should have said that it's projective. So you need to have f from x to z, say a projective morphism. And you will assume that L minus kx plus b is f nef and f big. So what does f nef mean? Again, it's sort of like being nef. L minus kx plus b intersect with any curve c should be non-negative. But now you're going to require slightly less. You're not going to require that this is true for every curve, but you just require that it's true for the curves that are contracted. If f lower star of c is 0. So that means for any curve, any vertical curve, the intersection has to be greater or equal to 0. And for the f big, you want that L minus. In other words, you could think of this as the restriction to every fiber is nef. And for the bigness, you want that the restriction of f to a general fiber an alternative point of view is pick a sufficiently ample divisor on z, pull it back, then you get something that's actually nef and big. And then your conclusion will no longer be on the cohomology groups. It will simply be on the higher direct images of OXL is 0 for every I greater than 0. So maybe the last thing I'll do is show you, clearly I'm not going to show you all of the consequences of Kawamata-Vivek vanishing in this context, but I'd like to at least show you one which is really useful and may make you more of a believer in some of the statements that I'll make later on, because some of them are proven in a similar manner. So there's a consequence of Kawamata-Vivek vanishing, which is known as Kolar-Shorokov connectedness lemma, or principle, I'm not sure, lemma. Connectedness lemma. So let's state it as a theorem. So f from x to z is a proper, let's just say, projective morphism of normal varieties with connected fibers. And we're going to assume that minus kx plus b is f nef, is relatively nef, and relatively big. Okay, so this is kind of sort of the wrong object, but it's reminiscent of Kawamata-Vivek vanishing. You'll see in a second how we apply it. And let's say every coefficient. So if I look at b, let me write for b less than 0, the stuff in b that has negative coefficient. Okay, so b, think of this as being b with positive coefficients minus b with negative coefficients. So I'm going to assume that this is f exceptional. I could even state it without the b, but it's actually much easier to prove if you state it this way. So the more complicated statement makes it easier to prove. You can ignore this for the time being if you want. Just a pair with positive coefficients, which is f nef, so a relative Fano situation. Then, when I look at the non-Kawamata log terminal locus of xb and intersect it with any fiber, this is connected for any z and z. So, e.g., z equals spec k. So this would be some kind of log Fano. Minus kx plus b is nef and big, and this would have to be empty. Then it tells you that the non-Kawamata log terminal locus is connected. So in some sense, well, we'll see later, it's telling you that this divisor here doesn't have too big of a volume in some mild sense. Okay, so the proof of this fact is just one page, and after that, I promise we'll take a break. So any questions about the statement? Anything that's confusing about the statement? Again, you could just, go ahead.
I think you didn't define the NKLT.
I did, but let me repeat it. The NKLT, oh, I didn't define the symbol.
Yeah.
NKLT is the non-KLT locus. So it's the union of non-KLT centers. So if this had simple normal crossing, it's everything with coefficient greater or equal to 1. If it doesn't have simple normal crossing, well, you have to go to log resolution. You look at everything with coefficient greater or equal to 1, and you take its image. That's the non-KLT locus, right?
So it can have components of various different dimensions.
The non-KLT locus could have components of different dimensions, except for the dimension of the variety. stupid reason. Okay, so.
You said something about volume. Would you repeat that? I didn't get that.
Okay, so mostly for the experts. If minus kx plus b had big volume, you'd expect to produce many, many sections. In particular, you'd expect to be able to produce interesting non-Kawamata log terminal centers. The more sections you have, the more freedom in choosing some auxiliary divisors you have. But no matter what you do, you're always going to construct something which is connected. And as we'll see later on, we're going to, on varieties genotype, we're going to play the opposite game, and we're going to produce interesting non-Kawamata log terminal centers which are not connected. So we'll get it.
So the statement is for final type varieties.
For final type variety, this is sort of putting a restriction on the geometry of final type varieties.
So you said connectedness implies the volume is not that big. Is that what you said?
In some sense, yes. So you could jack this up to use this to show that log final varieties are rationally connected. Right? So I'm not making any precise statement, but it is telling you something about the geometry of these guys. Okay, so this is sort of a weak statement, but it's a very useful one. Okay, so okay, let me not take too much time because we're going to take that break. So the first step is you have to think this through a little bit, but it's not complicated. We may replace x and b by a log resolution. So may replace x and b by some log resolution. So by that, what do I mean? Well, on the log resolution, you replace it by x prime and minus a on x prime, right? So in other words, kx prime minus ax prime is just the pullback of kx plus b. And everything that I said about x and b will be true for this pair. And so we're just going to prove it for this pair. And then the image of something connected is still connected. So this, it just follows immediately. So we might as well assume that xb is log smooth. So in particular, the non-KLT locus is just the stuff of coefficient greater or equal to 1. And now we're going to write a short exact sequence involving the stuff of coefficient greater or equal to 1. So let's consider the following short exact sequence. So here's a funny symbol, minus the round up of b. So what does this symbol mean? It's the same as minus the round down of b. It means that coefficient by coefficient, you're rounding them down or rounding them up, depending where you put it. So
it's not the same.
yes, it is. So let's try it. Let's try it with an example.
If it's an integer?
Well, it depends how you define it. So I believe it is the same. Let's try it. So let's try minus 1.5 and minus 1. So when I round this up, the round up of minus 1.5 is minus 1, and it's still minus 1, right?
Yes, yes.
And the minus this is the round up, yes, and minus the round down of 1.5.
I got it.
Okay. Yeah, but I haven't defined these, so there's a minus sign. Does everybody have an intuitive idea of what rounding up and rounding down an integer is? Okay, so when I do that to a divisor, I just do it component-wise. Okay, so now I map this into OX minus. So now I'm just going to consider those components of B which have coefficient less than 1, right? So you can think of B as being given by the stuff of coefficient less than 1 plus the stuff of coefficient greater or equal to 1. And then the round down of B will be simply the round down of the stuff of coefficient less than 1 plus the round down of the stuff of coefficient greater or equal to 1. I'm not saying anything interesting. But the point is that we have a minus sign here. So the map from here to here should be given by adding the divisor round down of B greater or equal to 1. So since that's a bit of a mouthful, let's call this divisor S. And so the co-kernel of this, X is smooth, so there's no tricky stuff, is this. And I should also mention, why are we picking rounding down the stuff with coefficient less than 1? Because we'll get something which is less or equal to 0. And hence, when you have a minus coefficient, it will be greater or equal to 0. Right? So this divisor is an effective divisor. This divisor is an effective divisor. Oh, not this one. This one. OK, now that you have this exact sequence, you're ready to read off the whole thing. So the claim is that R1 F low star of OX minus B is equal to 0. So why is that? We're supposed to apply Kawamata-Vivek vanishing. So I'm supposed to view this as something KLT plus something FNF and F big. The FNF and F big thing has to be, where did I write it? Has to be my minus kx plus b, right? So the minus kx plus b will have to play a role. So the trick is to view this as minus b is kx plus the roundup of minus kx plus b. So hopefully this will be completely trivial that I write down. Yes, this is completely trivial because kx is an integral divisor. So rounding up or rounding down makes no difference. I can take it out and they cancel. But now this is the same as kx minus kx plus b plus the fractional part of kx plus b. So when you think about it, this fractional part is going to kill the fractional part here, and you're going to end up with an integral divisor. What integral divisor? This integral divisor. But now you see that this is the FNF and big guy. And these two together, are a KLT pair. Because it's a smooth variety, this is an effective simple normal crossing divisor with coefficient strictly less than 1. It's a fractional part of a number, of a divisor, right? With simple normal crossing. So Kawamata-Vivek vanishing applies. It gives you this. So consequently, we have a surjection between the roundup of minus b less than 1 and the push forward of OS roundup of minus b less than 1 to 0. OK, so now, as I said, this is effective, right? So this guy here contains the push forward of O of S. OK, and this guy here is going to be also, well, effective, as I just said, and exceptional. So this push forward here is going to be equal to, by assumption, the map went to Z and it has connected fibers. So this is an effective exceptional divisor. So this is going to be of the form OZ. OK, so I'm getting a surjection from O of Z to F low star of O of S, right? Now, O of Z naturally just wants to map to O of F of S, right? Just by restriction to the image of S. So this surjection has to factor through here. So what does this say? This says, so how could it not have connected fibers? It would not have connected fibers if the push forward of O of S is strictly bigger than O of F of S, right? So if you had a 2-to-1 map, then the push forward of O of S would be sort of rank 2 over this guy. So that's not happening because this map, this guy is getting subjected onto O of Z and hence is getting subjected onto by O of F of S. Right, so the other inclusion is trivial. So this implies that O F of S is equal to F low star of O of S, which says that S to F of S has connected fibers. And that's what you wanted to prove. Okay, so let's take a break unless someone has questions. Yes.
I'm not quite sure. In the assumptions you said that b less than 0 is exceptional, but we never used.
Oh, yes, because at a certain point I said that the push forward of this should be O of z.
Yes.
But
That's b less than 1.
round down. So b equals to 0 is nothing, right? Because the coefficients are 0. So the round down of b less than 1
So the same thing as b less than
is contained in b, is the same thing as the round down of b less than 0. Other questions? And this playing around with the numbers and getting them just right can drive anyone crazy. And, yeah. Okay, let's take a 10-minute break. It's been going long. Oh my goodness, I know that too, and I
just going into language conscious.
no, but this is very nice. Well, listen, in Italy, we always say D-bag.
Yeah.
But I know it's D-bag, right? But it's just ridiculous. It's one of those things that. Yeah, I know, but you know. It's more annoying that I don't learn from my mistakes.
But in theory, of course, I mean, it's
Yes, that's true. But the second you said it, it's perfectly true. I've had people laugh at me before.
I mean, of course, I got confused with the round up and round down.
I know. Yes.
But this is really, when people working in this field, this must be nightmare. This is kind of calculation of the lesson.
Well, it is the same computation over and over. But you do spend an awful lot of time trying to make one specific thing appear with the number 1. Right? That's one of the games, because so here we got subjectivity onto something, and we're going to be doing that over and over again. And like if the image of that something is a point, then automatically it's globally generated. So then you're getting generation at that point. So that's why we play that game all the time. You sort of concentrate the singularities at the point, and magically you get a section. Is it any cooler outside?
Very warm outside, actually.
In which case I'll be right back inside. Because maybe it's easy enough that they can meet you at the Okay, great. You have back problem at looking? Yes. Me too. But I'm feeling better. You need to go to in over what I the whole conference. Yeah, what? Congress for interest of Natal. So we're ready now to talk about the calculus of non-KLT centers. So let's suppose that we have a log canonical pair. So traditionally, in a lot of papers, a non-KLT center on a log canonical pair is called a log canonical center. But I think we've all decided that that's slightly confusing, so I'll try to stick to the non-KLT centers. So there are going to be finitely many of these non-KLT centers, and here's the first property. Well, I forget if this is really necessary, but if you want an easy proof, so assume that there's another boundary, let's say B0, which is KLT. This may no longer be necessary, I forget. So what it means is that you can perturb this boundary to actually have something that's Kawamata log terminal. But maybe for some of the statements I'll make it will be necessary.
What is the relation between B and B naught?
There are just two divisors. So for example,
Contained in each other in some
not necessarily, but for example, if X itself was Q Cartier, canonical class of X is Q Cartier, forget about that. Then it's saying the ambient variety is KLT, but this pair, we've put an interesting divisor, multiplied it by its log canonical threshold, and now we have something that's actually log right at the boundary. Something interesting is going to happen.
It can be more than just modifying the coefficients of B.
Yes. So your typical intuition is B0 is not even there. It's nothing. KX itself is Q Cartier, and that's KLT. That's your intuition. So suppose that W1 and W2 are non-KLT centers, then so is W1 intersect W2. I have to be a little bit careful. W1 intersect W2 may have many components. Each component of the intersection of W1 and W2 is also a non-KLT center. What's the intuition behind this? You have two non-Kawamata log terminal centers, W1 and W2, which means that above that you have two divisors, E1 and maybe E2, which both come with multiplicity 1? Well, the intuition is that then there has to exist some other divisor with center, this point here. Okay, so my picture is horrible, but here's my other divisor, okay? So this is my divisor F, which has center over this point here. Why should I expect that such a divisor exists? Well, I know that if F is not there, the picture is wrong because we have this connectedness result that we applied, right? Because here is your pair XB, and here is your log resolution. Let's call it X prime B prime, where B prime is just obtained from the pullback of this. Then these coefficients are appearing in B prime with coefficient 1. The stuff with negative coefficient is clearly going to be exceptional for this map. So, and Kx prime plus B prime is the pullback of Kx plus B. So it's F trivial, but for a birational map, F trivial means F nef and F big. So this is one of the situations in which the connectedness theorem applies. So you can't have a situation in which the only two divisors over W2 and W1 with coefficient 1 are disjoint. Because then the fiber over their intersection would be empty. We know that's not the case. So these two divisors either intersect or are connected by some other divisor of coefficient 1. And if you think about that carefully, that is what's going to give you the center living above the intersection. So I haven't proved it, but we have a good intuitive idea why it should be true. So the consequence of this is, so for any x in the non-KLT locus of xb, there exists a unique minimal non-KLT center. And these minimal non-KLT centers, they're well behaved. So if W is a minimal, I'm sorry?
Or any
there exists a minimal non-KLT center, X in W contained in the non-KLT centers of XB. So I mean a minimal non-KLT center going through that point. If W is a minimal non-KLT center, let's say it's just minimal at each of its points, then W is normal, and Kx plus B restricted to W is nice. So there's some nice adjunction. So let me try and explain the adjunction result. What's this adjunction? So, well, let's say before I state the Kawamata subadjunction result, so one thing I did mention, so if S contained in B is a smooth divisor on a smooth variety, then this is a minimal log canonical center of the pair Kx plus S, and when we restricted this to S, we get the canonical class of S. So that's definitely nice. If now S, let's say if X B is log canonical, and the multiplicity along some divisor S of B is equal to 1, so S is a component of B of coefficient 1, then Kx plus S restricted to S is of the form K S plus this different. And this different, I told you, has coefficients of the form 1 minus 1 over K, where K is an integer, positive integer, or possibly infinity. But if we assume that if S is minimal center of log canonical singularity, then actually the coefficients of this, the pair S different is KLT. So the coefficients are strictly less than 1. I'm trying to make the argument that minimal centers are better behaved. So in general, what's true, we have something known as Kawamata subadjunction. So Kawamata subadjunction says that if W is a minimal non-Kawamata log terminal center of the pair XW, of a log canonical pair XW as above, then we can write Kx plus B restricted to W is of the form. So what we would like to say is of the form KW plus BW, where this is a Kawamata log terminal pair. In Kawamata's original formulation, you actually need to, so first of all, it's not equal, it's Q-linear equivalent. And you actually need to modify this. You need to sort of make things a little bit more flexible. You need to add arbitrary small multiple of an ample divisor. So is it now known to hold without the arbitrary small multiple of the ample divisor? Does Kawamata subadjunction actually hold nowadays without the, right? So is that Yu and Gongyo? Yeah, okay. So by a result of Fujino and Gongyo, see this thing that I wrote really small, you don't actually have to worry about it anymore. It's a non-trivial result. Okay, so even Kawamata subadjunction, the original formulation, is highly non-trivial. It's, for the case of divisors, it's quite easy. For the case of higher dimensional, codimensional subvarieties, it's quite hard. What you have to do is you have to look at this non-Kawamata log terminal place, this divisor living over W, and you have to write a canonical bundle formula for the map from that divisor to the center, which is a higher dimensional generalization of Kodairo's canonical bundle formula for elliptic curves. And it's,
what is the definition of BW on the right-hand side?
Oh, it's a complicated object.
Oh, complicated.
So I can tell you.
No, that's okay. It's not, okay. Because restriction is not defined there.
Right. No. You have to go look at the. So you
something special.
You have this variety X, and inside it you have this W. You look at the log resolution, and you have, let's say, X prime, and you have a special divisor E with coefficient 1 that's mapping onto W. Now you look at that setting there. So now you see that K X prime plus B prime, which contains A with coefficient 1, is the pullback of Kx plus B. So it's trivial for that map. Right? So it's kind of like an elliptic fibration. When you restrict this to any fiber, it's Q linear equivalent to 0. So you could hope, so you could hope that when you restrict this, so kx prime plus b prime restricted to E, this is a friendly gadget. You're just restricting to a divisor upstairs. Maybe you even assume that this has simple normal crossings. This is a friendly operation. Now you want to solve, you know that this is Q linear equivalent to the pullback of some divisor on W. L is a bad choice. G on W. And you want to solve, you want to be able to write this as a canonical class of W plus a divisor B. And that's a mixed object. It's actually a boundary part, which measures the singularities of this map. And then it's a moduli part, which measures the variations of the fiber of this map. So for example, when you had Kodairo's canonical bundle formula, the singular fibers have some contribution, and then there's this pullback, 1 over 12 pullback of O of 1.
So this exists, right? BW is not quite uniquely determined.
It's absolutely, it's only as a Q divisor, up to Q linear equivalent.
Yes.
And in fact, that's what I was trying to explain here, is that just as in Kodairo's bundle formula, the part that's coming from the singularities is really uniquely determined. It comes from the singularities, and the coefficients are really well understood. This part here is sort of mysterious.
Yes.
It's 1 over tau of the pullback of a hyperplane,
Yes.
right? So, you know,
No.
it's that kind of feeling, except it's worse. You can't say it's a pullback of a hyperplane. You can say it's a Neff divisor. So that's why originally Kawamata added epsilon ample. So this is quite a beautiful but quite complicated story. And then the improvements that allow us to remove that are even more complicated. Okay, so now I'm ready to talk about multiply ideal sheaves, which is the last technical thing I need to talk about before we start with the proofs. So definitely, if I don't do some today, I can definitely start with them at the beginning of next lecture. So maybe to put ourselves in a slightly more friendly setting, I'll pretend that the ambient variety is smooth. And what I want to do is I want to define multiply ideal sheaves. So let's assume that X is smooth and B is some effective divisor.
I'm sorry, I don't. Can you give me some example where if it's not minimal, it fails to be normal?
Gladly, because it's so easy.
That's so easy.
You take C2, and you take your divisor is the union of two lines. Then you see in this picture, the two lines with multiplicity 1 are, that's the whole non-Kawamata log terminal locus. They are not normal.
Oh, I see.
Or here's another, okay, maybe a better picture. There.
I see.
So
I see. Oh, okay. Sure.
I don't know. You may argue locally, analytically, but okay. Okay, so now I've sort of shifted slightly gears. I'm talking about multiplier ideal sheaves. We have a pair XB, but I'm assuming that X is smooth for simplicity. You can do it more in general, of course. And the multiplier ideal sheaf is always also defined in terms of a log resolution. So F from Y to X is going to be some log resolution. Then the multiplier ideal sheaf, I, which depends on X and B, is a push forward of OY, KY over X minus the round down of the pullback of B. And yes, I understand that if you're not used to working with these round downs, it's not very nice, but this is an R divisor. When you pull it back, it's still an R divisor. In order to make this into something, a sheaf that you can push forward, you have to do something like that, right? Either the round down or the round up. Those are pretty much your only choices. So now, the first thing we observe is that clearly this is contained in the push forward of OY KY over X, right? This B is an effective divisor, so its pullback is effective. The round down is effective. Minus that is, you have an inclusion from here to here just by adding this effective divisor. So this ky over x, since I assume that x is smooth, this is an effective and exceptional divisor automatically. So this push forward is automatically O of x. Hence, this is clearly an ideal sheaf. The name multiplier ideal sheaf. Well, multiplier is unclear why we are calling it a multiplier ideal sheaf, but at least an ideal sheaf, it's clear. So it's an exercise that this is independent of the given log resolution. Just like checking Kawamata log terminal and log canonical was independent of the log resolution. And in fact, it's immediate to check that I is trivial if and only if the pair XB is Kawamata log terminal. So let's think about that for a second. What does being Kawamata log terminal mean? It means that the corresponding coefficients are all strictly less than 1. Coefficients of what? Well, so when you're computing the coefficients, you're looking at, you're comparing, maybe you're writing ky plus the corresponding divisor on y as the pullback of kx plus b, and you're saying that these coefficients have to be strictly less than 1. Okay, so that's not what we wrote up here, so we sort of have to unravel it a bit. So let's see. Here we wrote ky over x minus the pullback of b. So ky over x, that means ky minus the pullback of kx, minus the pullback of b. Let's not round down yet. So I'm taking this part to the other side. That's minus by. Oh, that's my discrepancy divisor, right? So now I'm taking the round down of minus that. That's the same thing as the round up of the whole thing. So this is the round up of this. So that's the same as the round up of this discrepancy divisor ay. Okay, so saying that it's KLT means that the coefficients of ay are greater, strictly greater than minus 1. So the coefficients of the round up of the whole thing are greater or equal to 0. So saying that it's KLT is precisely saying that this divisor is effective and exceptional, which is equivalent to saying that the push forward is indeed equal to O of x. So it's just an exercise in unraveling the two definitions and not messing up the round downs or round ups of the divisors. Not getting confused with that. Okay, so another situation in which it's very easy to calculate multiplier ideals is when you have B a simple normal crossing divisor, then clearly the ideal of XB is just OX of minus the round down of B. Why is that? Well, if B has simple normal crossing, you don't have to do any work. No log resolution is needed. The identity map is a log resolution. The relative canonical is trivial. There's no pullback. You're just doing minus round down of B. By definition. There's no work to be done. Slightly more work needs to be done to check the following thing. It's just the projection formula. So suppose that G is Cartier. So on a smooth variety, Cartier just means that you have integral coefficients, positive integral coefficients. Then that will imply that the multiplier ideal of G plus B is the same as the multiplier ideal of B tensor by OX minus G. Right? So this is locally free sheaf. So this is not locally free, but tensoring by locally free is exact. So that's not intimidating. This is a line bundle. And this is really just a projection formula, because when you write this gadget, you would have a minus f upper star of G, which comes out of the round down since it's integral. And then projection formula is the same thing as the push forward of this tensor OX of minus G.
So G is effective.
G Cartier and effective. If it's,
Because he's defined.
yeah. At the very minimum, I have to insist that G plus B is effective. Otherwise, this symbol does not make sense since I haven't defined it. You can do it in general. Then you have to talk about fractional ideals. And I don't need that, so let's just keep the settings slightly more friendly. Another triviality is that if D1 is less or equal to D2, of course effective, then the multiplier ideal sheaf of D1 is, well, which way should it go? So let's see. Which one of these two will have worse singularities? The bigger divisor corresponds to worse singularities. So it could happen that this one is KOT and this is not KOT. So this will have non-trivial ideal and this will have trivial, meaning equal to O. So the inclusion has to go this way. So deeper ideals correspond to worse singularities. Maybe I should say, I should emphasize that. I of D measures singularities. Deeper ideals equal worse singularities. Okay. Now, another thing that's very easy to check is suppose that the multiplicity at some point x of your effective divisor D is greater or equal to n denotes the dimension. Then this tells you that the ideal is non-trivial. This tells you that the multiplier ideal sheaf of D is contained in the maximal ideal of x. It cannot be trivial. It cannot be the whole of O. The corresponding metric is not integrable at that point, if you know the analytic language. The proof of this fact is also easy. You look at your resolution, y to x, and since it works for any resolution, you may assume that this resolution factors through the blow-up at x of x. Now, the blow-up of x at x contains one interesting exceptional divisor that maps to the point x. Now, the coefficient, let's compute a along e of x b. Well, we get a contribution from the class from the relative canonical divisor, which is the codimension -1. So you get n minus 1 copies multiplicity will be n minus 1. This is coming from the relative canonical divisor. Minus, what contribution do we get from b? Well, we get precisely the multiplicity. You could think of that as your definition, right? When you blow up at the point, the pullback of b will be its strict transform plus the multiplicity at the point times the exceptional divisor. So minus the multiplicity at x of d. And this, by assumption, is less or equal to -1. The multiplicity is greater or equal to n. So it's not going to be, we have one discrepancy that's less or equal to -1, one bad discrepancy. That's enough to rule it out. It's not a KLT pair. The multiplier ideal has to be non-trivial.
So B is equal to D.
Thank you. No, I appreciate that because I hate writing stupid things. Oh gosh, and so then D is really equal to B. No, yeah, you're right. You're right. I had one wrong, then I started changing the wrong one. But the divisor in question is D or B. Is the same. So something that's slightly harder, but not much harder, I'll discuss in a second when I tell you about restriction of multiplier ideals, is that if the multiplicity at x of D is less than 1, then the multiplier ideal sheaf of D is actually trivial, while at least locally near this point x. So the multiplicity is less than 1 for every point on your variety, then it's truly trivial. So I'll show you in a few minutes. A trivial fact is that the log canonical threshold of the pair, well, I'd have to say x with respect to the divisor b is the same as the supremum of those t's such that the multiply ideal sheaf of x, comma, tb is trivial. There's nothing to this because being Kawamata log terminal is the same thing as having trivial multiply ideal sheaf. So this is just a rephrasing. You can measure being Kawamata log terminal or log canonical in terms of the multiply ideal sheaf. And so you can also compute the log canonical thresholds in terms of multiply ideal sheaves. Yes? Oh. Really?
If you have some smooth divisor, but then like really tangent at that point,
Right.
the multiplicity is less than 1. The singularity is really bad. So even in that case, multiply ideal sheaf is...
You are mistaken. Because what you have in mind is sort of some adjunction thing. So we'll do it in a second. You see, it could happen that you have something like this with coefficient 1 minus epsilon along a divisor, and then something very tangent.
That's right.
But see, this 1 minus epsilon, yeah, you're right. So it's subtle. Correct. Yes. So you're saying, well, you haven't made any precise statement, so it's hard for me to...
No. The statement is, suppose it's 1 minus epsilon. That component, tangent, is slightly smaller than epsilon.
Right.
And then tangency is really bad. Even in that case, multiply ideal sheaf is trivial.
It's making, I mean, I'm not going to use this fact. It's making me slightly worried, but I have a proof in mind, so I shouldn't get...
Sorry about that.
So I'm going to address this situation exactly in a second. So if I said something wrong, maybe we'll see it. But so certainly I'm taking this statement from Rob's book.
It's true.
Yeah, this
Okay, sorry.
This statement, I'm taking it from Rob's book, and I know a proof, and I'll try to tell you a proof. So it's most likely true, but I understand exactly what you're saying with this example. So it must be that...
So in this case, as long as the multiplicity is smaller than 1, the multiplier idea does not reflect the singularity.
Yeah, so I think what you're going to need to do with this is really you need to add sort of epsilon times the multiplicity at that point.
I will check. Sorry about that. That was just a question.
No, but I understand exactly where you're coming from. Okay, so now it's time to state Nadel vanishing, which is just a rephrasing. So you may wonder why bother doing multiply ideals? It's essentially the same thing as Kawamata log terminal pairs, log canonical pairs, that kind of stuff, right? And now I'm going to rephrase Kawamata Vivek vanishing in terms of multiply ideals. And you may be wondering why doing that. Well, because it's a lot easier to produce sections that don't vanish at a given point with this. So we'll do that in just 1 second. So technically, it's a very useful tool to have. You can certainly do everything in the minimum model program without Nadel vanishing, without multiply ideal sheaves, but then you have to worry a bit more about keeping track of these round downs and round ups and coefficients being exactly equal to 1. Okay, so here's Nadel's vanishing theorem. I guess sometimes people refer it as Kawamata Vivek Nadel vanishing. So X is going to be smooth. D will be some effective R-Cartier divisor, R divisor. F will be a projective morphism. N will be some Cartier divisor such that N minus D is F nef and F big. then higher direct images of OX KX plus N tensor I of this. I called it D, hopefully D. Maybe one more parenthesis, 0 for every I greater than 0. Okay, so how does this compare to Kawamata-Vivek vanishing? Well, Kawamata-Vivek vanishing did not have the multiply ideal sheaf here, but it had one extra assumption. It's essentially the same, except that I called Kx plus N is what I called L in the previous statement. It's essentially the same, but I had one more hypothesis. I had the hypothesis that X comma D was Kawamata log terminal, right? So if I of D is trivial, this is equivalent to Kawamata-Vivek vanishing. But as you'll see in a second, this is slightly an overstatement, because if you buy Kawamata-Vivek vanishing, then this is an immediate corollary. So I'll write it down as a consequence in a second. So anyhow, you think of this sort of as a correction term that you need to put in there if you want to have these vanishing results. And at first glance, you think that it's a nuisance. Your first reaction is, if only this guy weren't there. But actually, you really want this guy there. That's what makes the magic happen. So let's prove what? Prove Nadel vanishing using Kawamata-Vivek vanishing. How can the proof go? Well, there's a multiply ideal sheaf here. So in order to make that appear, we necessarily need a log resolution. And so let's try and write down a log resolution, and let's just apply Kawamata-Vivek vanishing to the log resolution. So let's give ourselves some log resolution. Of everything inside. And then, in order to apply Kawamata vanishing, I need some FNF and so I have N minus D as FNF and F big. So let's look at the pullback of N minus D. And let's observe that then this is F composed with G, Nef and big. Well, the Nefness, it needs to intersect curves non-negatively. Well, clearly, the only new curves you really have to worry about are curves that are getting contracted from y to x, and those automatically intersect this 0. And as a map from y to x, this is a birational map, so this is automatically big from here to here. So I'm really not saying anything. And so, in fact, so by what I just said, it's trivial that this is also G, Nef, and big. Right? So there's certainly less curves to check, to intersect this gadget against to check that it's G Nef, and G big is just a birational map. There's nothing to it. So by Kawamata-Vivek vanishing, what do we get? We get two things. We get that if I push forward, ky plus the roundup of the pullback of n minus d. This is equal to 0 for every I greater than 0. And Ri F composed of G lower star of Oy, the same thing, ky plus roundup of F. Oh, this is supposed to be G, isn't it? G upper star of n minus d is equal to 0 for every I greater than 0. So I have to check that Kawamata-Vivek applies to this. Well, what is the roundup of this? The roundup of this is G upper star of n minus d, which is F Nef and big, or F composed G Nef and big, plus some fractional. Right, so if the coefficient of this guy is like 2/3, then the fractional part will have coefficient 1/3, whatever you need to make it 1. It's going to be strictly less than 1. It's a log resolution, so it has simple normal crossing. So this part is F, Nef, and big. This guy plus this guy is a Kawamata log terminal pair. So Kawamata Fivek directly applies there. No, you just read it off immediately. So both of these are 0. So then, by the usual spectral sequence argument, a trivial spectral sequence argument, the corresponding Leray spectral sequence is degenerate immediately at the E2 term. What you get you don't even need spectral sequences to prove this, but what you get is that G lower star, F lower star of G lower star of OY, KY, plus the round up of G upper star minus D is equal to Ri F composed G lower star of the same thing, which is 0 for every I greater than 0. Okay, so I have maps from Y to X to Z. I start with one sheaf here, all of whose high direct images are 0. Then the only one that survives is the push forward of the sheaf, and the high direct images of that have to match the high direct images via the push forward for the whole thing. This is sort of a standard argument. So while my claim is that something is equal to 0, I have 0 on the right side, so it looks like I'm on the right track. So I have to check that this thing on the left side is what I need. Well, here I got the RIF lower star, so that's good. So is this thing inside that? Okay, so now we are going to use the projection formula. You see, n is Cartier. So it has integral coefficients. So this thing here is the same as doing G upper star of n plus the round up of minus D. By the projection formula, this whole thing is the same as OX KX plus n tensor G lower star of OY KY over X. The Y over X, if I add KX, I also have to subtract the pullback of KX here. And then plus the roundup of minus D. And hopefully, this matches my definition of the multiply ideal sheaf of D, so which I hopefully haven't erased. Oh, it looks slightly different because I have minus the round down of the pullback. But you see, that allows me to discover my typos. So first of all, I had a G upper star, which I didn't distribute. And secondly, the roundup of a minus G upper star of a minus a divisor is the same as minus the round down of that divisor. And now, hopefully, it's really matching the definition. Okay, so that's how you go from Kawamata Fivek vanishing to Nadel vanishing. Okay, why is Nadel vanishing so useful? So the typical goal in algebraic geometry is to show that some divisor, say mkx, say if kx were nef and big or something, under some assumption, you want to show that some linear series is base point free. This is a typical, very lofty goal. Okay. Some multiple of some divisor in some effective way has sections. So that guy, or maybe something of the form kx plus n is generated at some point x in x. So what's one example where something like there's a big theorem that smells like this. So e.g. there's this big result due to Anhan and Hsu, which states the following. So X is smooth. There are stronger versions, but let's say A is ample. Then Kx plus Ta is generated, is base point free, for every integer t greater or equal to, okay, let me play it just slightly safe. N plus 1, choose 2, plus 2, it might just be plus 1. Plus 1 should be enough. Okay? So how would one prove such a thing? This is literally what they do in the proof. The main idea, find a divisor D, which is linear equivalent, Q linear equivalent, to a multiple of A, where this multiple is less than n plus 1 over 2 plus 1, such that, okay, so I want to show it's base point free. So for any x in X, you want to find a divisor such that the multiplier ideal sheaf of D is equal to the maximal ideal of X locally near the point X. You don't need this to be true on the whole variety, but you want to produce that point as an isolated point in the co-support of this ideal. So you don't actually need to even produce the maximal ideal. As long as you produce some scheme of length 0, it automatically follows. But you can always do this. Why do you win? Because then...
You mean lambda is bigger than or equal to?
No, I want it to be smaller.
Small.
I can certainly do it for lambda bigger. I use sort of self-vanishing, right? If I'm allowed to take an arbitrary big multiple of an ample line bundle, I can do anything I want, right? So I want to produce a controlled multiple of the ample divisor with some interesting property with a nice multiplier ideal sheaf. Picks out this point here. Then you see, by Nadel vanishing, higher cohomology groups of Kx plus Ta tensor the multiplier ideal sheaf of D are equal to 0. You see, the only thing I have to check is that, so I should say for every I greater than 0, the only hypothesis I really have to check is that Ta minus D, this is Q linear equivalent to T minus lambda A, where this guy here is positive by my assumption because lambda is less than T. So this is ample, in particular in F and big. So it applies. So we have vanishing of these higher cohomology groups. Then this means, by the corresponding short exact sequence, so we have the short exact sequence, I of D goes to O of X, goes to O of X mod I of D, goes to 0. A summand of this thing here, a summand is O of X modulo maximal ideal. Let me call this the skyscraper sheaf at the point X. So I take this short exact sequence, I tensor it by Kx plus Ta. So what I'm getting is that H0 of Kx plus Ta surjects onto Ox Kx plus Ta tensor C of X. The next group will be H1 of this tensor the multiplier ideal sheaf, which is 0. Right? So, okay, so typically you sort of just suppress this. You think of this as evaluation at the point. And what it's saying is that this map is surjective, so there will be a section in here that does not vanish at the point. And if you can do this for every point, you've shown that that linear series is base point free. If you want to show that a certain linear series is birational, well, then you have to be able to pick two general points and show that you have a section that vanishes at one but not the other, and vice versa. So you have to be able to play this game with two different points. Well, if you can play it with 1 point, it's pretty believable you can play it with 2 points. Separating tangent directions is harder. We won't need that. That's a harder business. Okay, so once it's stated this way, the goal is to produce multiply ideal sheaves that are supported at points. So this is not necessarily easy. We'll need some tricks. So it's not hard to produce non-trivial multiply ideals. You just produce a divisor with Hahn multiplicity at a point. That's easy to do. The problem is that the multiply ideal sheaf may be much smaller than m of x. It may have a whole subvariety. Then you need to cut down the dimension of that subvariety. So let me say the last 2 words about multiply ideal sheaves, then maybe that would be a good place to stop. And we are set up in such a way that we can actually start discussing some of the weaker versions of the boundedness result at the beginning of the next lecture. So the last things I want to say about multiply ideal sheaves is they're related to a junction. They're related to how can I make a multiply ideal sheaf smaller. So the setting I want to think about is X is smooth, H is a smooth hyperplane, a smooth divisor. D is going to be some effective divisor, R divisor, and I want that the support of D does not contain H. So I want to be able to restrict it to H. Kind of like the picture that Matsuki made me draw.
Can I ask a question?
Yes.
So after all, Nadel vanishing, if after you blow up, is Kawamata feedback vanishing?
Yes.
Is there any actual merit of looking at the multiply ideal sheaf to consider the Nadel vanishing theorem? So,
as I said, you could do everything with Kawamata-Fivek and keeping track of your log resolution and keeping track of some divisors that appear with coefficient greater than 1.
But is there any advantage of staying on the original variety?
Psychological, there's a huge advantage. In practice, in the computations I do, of course, you know, Nadel vanishing is more of an analytic point of view. Then you have one that's also associated to metrics, and you can actually do more stuff with that than we can do algebraically. Like these deformation invariants of plurigenera in the non-general type case.
So there is a merit. There are merits.
Yes, but you have to consider the multiply ideal sheaves for metrics, for example. Or you can prove abundance and then pretty much you don't need that stuff anymore, but yeah. Okay, so what do I want to say? I wanted to tell you something about the restriction. So let's look at the multiply ideal sheaf of on H of the divisor D restricted to H, and let's compare this to the multiply ideal sheaf on X of D. Well, these are two, I cannot compare them. This is a sheaf on H, this is a sheaf on X. So I can take the sheaf that this guy generates on H, right? So I restrict these functions to H and takes the corresponding subsheaf of O of H. And how do these compare? This way. So if you take a divisor and restrict it to a subvariety, you get worse singularities possibly than if you look at the divisor on the ambient variety. Here's a picture. You take, this is my H. This is my divisor D, for which I'm taking coefficient 2/3. Then the multiply ideal sheaf of D, of X comma D, is just O of X. So the right-hand side is just O of H. Not interesting. But the left-hand side is the multiply ideal sheaf on H of D restricted to H, which now you see, since it's tangent, it has, when I intersect it, I get this point with multiplicity 2. let's call this point O, or P, maybe it's easier to see. I get this point with multiplicity 2, and this has coefficient 2/3, so this is a multiple ideal sheaf of 4/3, this point, so this is just OH minus P. I have to round that down. So the inequality can indeed be stripped. It's an equality if everything has simple normal crossing, then you don't have this annoying phenomenon that the multiplicity jumps up. Okay, so this is sort of the trivial direction, sort of adjunction direction. The interesting direction is the analog of inversion of adjunction. So suppose that I know that the multiply ideal sheaf on H of 1 minus S D restricted to H is contained in Mx for some S which is less than 1. Okay, so if S were equal to 0, then I'm saying that this restriction is not Kawamata log terminal. But now the coefficient 1 minus S is slightly less than 1. So I'm really saying that the restriction, what this is really saying is that the restriction of D restricted to H is not Kawamata log terminal. Even when I make its coefficient a little smaller, it still has non-trivial. Sorry, it's not log canonical. Even when I make its coefficient smaller, it's, so i.e. H D restricted to H, not log canonical. Okay. Then the multiply ideal sheaf of X D plus 1 minus T H is also contained in M of X for any sufficiently small t. So I'm assuming that I have some bad singularity on this divisor. Then I get some bad singularity on the ambient variety. Well, not for D itself. I need to do D plus this copy of H. 1 minus something, but almost the whole copy of H. So the analog in terms of log pair, or the similar result in log pair, is sort of easier to digest. And we've essentially proved that already. So let me state that. But this one is the form in which it's sort of a bit easier to use. So the analog for log pairs is the following. Suppose that you have a pair, and this x plus s plus b, this is just some pair, let's say with non-negative coefficients. Then x s plus b is log canonical, respectively PLT. PLT means that the only thing with coefficient 1 that ever appears is the divisor s itself. Everything in B has coefficient strictly less than 1, even after I blow up. So it's a sort of one of these intermediate variants. Log canonical I already defined. If and only if S B sub S is KLT. Now you may worry, is S normal? Does this even make sense? So B, and what do I mean by B sub S? So if S is not normal, replace it by its normalization. I don't want to add sort of the extra technical condition. If it's PLT, one can show that it's automatically normal. So it's a minimal log canonical center, it's automatically normal. If it's log canonical, it may not be normal. What does this BS mean? You write KX, as we did before, plus B, S plus B, restricted to S. It's a divisor, a junction is easy. It's KS plus B sub S. That's what I mean by B sub S. So here it should read is log canonical slash KLT. So the log canonical statement is highly non-trivial. It's due to Kawakita. It's a nice result of Kawakita. But the PLT versus KLT statement is actually relatively easy to see. So maybe I'll illustrate that so it'll become clear what we're saying. So how do you check that something is log canonical or PLT? Again, you go to a resolution. Here you have your divisor S, and you have some components B, which I'm not going to draw in the picture. Well, okay, you have S plus B here. Then you take a resolution, X prime. You have a new divisor S prime, and you have some boundary divisor B prime. Okay, now, saying that it's PLT means that precisely that for any log resolution, the coefficients of this B prime are strictly less than 1. Or the coefficients of the discrepancy, which is minus that B prime, are strictly greater than -1. Okay, but then you see when I restrict to S prime, since we are in the simple normal crossing situation upstairs, then clearly if I do Kx prime plus S prime plus B prime restricted to S prime, this is of the form Ks prime plus some divisor. Well, we know what it is. It's B prime restricted to S prime. It's simple normal crossing. These coefficients are also less than 1. They're the same coefficients as these coefficients, just we forget about those components that do not intersect S prime. So now you just observe that this guy here is the pullback of, essentially by definition, of Ks plus Bs, right? Because Ks plus Bs is the restriction of this gadget. The pullback of this gadget is this guy. So just by commutativity of the diagram, that's what you get. So that means that SBs is KLT. I told you a junction was easy. We didn't have to do any work. We just had to write down the definition and observe that if the ambient pair is PLT, then the restriction to the divisor is KLT. The interesting thing is inversion of a junction. It could happen that when you look at, a priori, it could happen that when I look at the coefficients of B prime, I have one coefficient which is maybe 2/3, and I have another coefficient which is 1. And this coefficient which is 1 does not see S prime. Right? So it could happen, sort of your nightmare scenario is that this guy is KLT, all of the coefficients nearby are strictly less than 1, but there's some coefficient far away which is greater than 1. But this cannot happen by the connectedness lemma. Right? The connectedness lemma tells us that everything in the non-KLT, every the non-Kawamata log terminal places intersect with any fibers, give you a connected locus. Well, you see, in this situation, you have a point down here whose, when I look at the fiber over this point, well, it intersects something of coefficient 1, namely S prime. It intersects something else of coefficient 1, this component that I'm imagining to exist. And so there must be other components of coefficient 1 which actually connect with S prime. Right? So there has to be, if there is any component of coefficient 1, even if it doesn't intersect S prime, it forces the existence of other components that do intersect S prime just by this connectedness lemma. So this is a very surprising feature, this inversion of a junction. And so when you package it in multiply ideal sheaves, it is this statement here that I made.
I have two questions. So that's for all S or some S?
Some S.
Some S.
For all T sufficiently small.
Okay, yeah, that's one question. And the second question is, how do you know if S is normal?
Okay, so if it's in the PLT case, it's a minimal center of log canonical singularities.
You're right.
By definition of PLT,
You're right.
and so
Yes.
we're good.
Yes.
If it's in the log canonical case, it's not true, so we have to work on the normalization.
You're right, yes.
It's not too scary.
I see. Thank you.
Any other questions? This is all I plan to say for today.